Hi, everyone. So for the next 8 minutes, I invite you to pull up a chair beside your favorite permanently shadowed crater, and we will consider a rim-side view of cold-trap volatiles released by micrometeoroid impacts. My co-authors on this presentation are Mehdi Bena and Menlia Sarantos, who are always great people to work with because they ask excellent questions and then they bug you just enough that you actually get the work done. The motivating question behind the work that I'll talk about today is a straightforward but also an interesting one, and that is, what would you see from the rim of a permanently shadowed crater? We know that at least some permanently shadowed craters contain ice, and we know that there are several processes that act on those on any ice in those craters that can cause those volatiles to be ejected onto surrounding terrain. Micrometeoroid impact, sputtering, there are various processes that can cause that release. And so if if you were perched on the rim of one of these regions, if you had an instrument on a lander or rover, deployed instrument like Ludley LACE on Apollo 17, if you have an instrument that's sensitive to volatiles either in the exosphere or on the surface, this could be a way to characterize the composition of cold-trap volatiles and the processes that act on them without having to venture into the thermal and illumination extremes of permanent shadow. This is, like most things, this is something that was previously studied by Bill Farrell, Dana Hurley, Mike Zimmerman in their 2015 paper. And so what's new in the work that I'll present today is that since then, thanks to measurements by the LADEE mission, we have an updated understanding of how micrometeoroid bombardment operates globally and at the poles. And so we use an updated source rate for released water, and then we wade a little further into that parameter space. Our approach is to carry out a Monte Carlo simulation. So a global scale, so a local version of the global simulations that Kennedy talked about. So we release water molecules, a large number of representative water molecules from both within a PSR and from its surroundings. And then we look at where those water molecules fall back. And so for the purposes of this work, we assume that a PSR is a cylindrical depression with a specified depth and diameter. We assume a certain rate of release of water from non-PSR terrain. So this could be a subsurface reservoir that's probed by micrometeoroid impacts, and we assume a value of the rate of release of water based on LADEE measurements. In the PSR itself, we assume that water is closer to the surface and it's present in higher amounts. And so we assume that the rate of release of water from the PSR is 1,000 times greater. And if you do the math, that's consistent with assuming a few weight% of water. So the water molecules are released uniformly in all directions with a velocity distribution that depends on a temperature that you can specify. And another important thing to note is that we really are only modeling that release and fallback. So for instance, we're not considering how those molecules might migrate after they land. And so if you put all of that together, you get a picture that looks something like this. So in this case, we assumed a Shackleton-like crater in the center, and we sampled that velocity distribution from a temperature of 4,000 Kelvin, which is what you would expect for micrometeoroid impacts. And the colors on this plot show the downward flux of H2O. So this is how much H2O in terms of number of molecules per square meter per second is falling back, both within the PSR and to surrounding terrain. And so if you look at the magnitudes of that flux, the downward flux is several orders of magnitude lower than the flux out of the crater. And so the point there that it's a small but still noticeable fraction of water that falls back to the surrounding terrain. And one of the interesting things, I have some nominal PSRs outlined in white there. And so if you think of the spatial scales here, you'll notice that some amount of water from a PSR could fall back to other PSRs. And so there's this sort of interesting light mixing process that might be going on there. We can also look at this in a different way. So this is that same flux as a function of radial distance from the center of the crater. And these solid lines are a case where there's no topography. And the dashed lines are a case where we account for the presence of a crater wall so that not all of the molecules that are released make it out of the crater. And so several interesting things to note here. One is that within this entire 75-kilometer region that we simulate, the downward flux of water is dominated by the PSR, even though we have smaller amounts of water released from the surroundings. The signal from the PSR really swamps that across this entire region. You will also notice that including the presence of a crater wall results in quite a significant reduction of the flux in the surrounding terrain. And we'd expect that to be more pronounced if you have a deeper crater and less pronounced if you have a shallower crater. In terms of comparing to previous work, the magnitudes that we see here are comparable with the earlier Farrell et al. Work if you scale those to account for a higher source rate, which we think may be the case. One of the things that's different is that we see a more gradual drop off in the flux with distance from the crater than Farrell et al. Did, and that might be due to some of the specifics in how we set up the simulation. And I'm happy to talk more about that if folks want to get into that. We can also look at how different parameters influence this. So on the left is our baseline case where we have H2O released at a temperature of 4,000 Kelvin. In the middle is H2O again. This time it's released at with a velocity distribution corresponding to a temperature of 500 Kelvin, which is what you might expect for a slower L-cross-like impact. And then on the right, we have a 4,000 Kelvin velocity distribution, but this time we're looking at a heavier molecule. We're looking at CO2. And you'll see that there are differences between those three cases. And ultimately, the reason for those differences is because, as you can see in the line plot, which shows velocity distributions, both temperature and molecular mass affect the initial distribution of molecular speeds. And that, in turn, is what affects the distribution of where and how far away stuff falls back. And so a couple of the interesting things, both reducing the temperature and increasing the molecular mass increase the flux of molecules that fall back. Fewer of them are likely to escape lunar gravity. Another one of the interesting things is if you compare the H2O and the CO2. So this was a case in which we assumed that the mass flux out of the crater was the same for both those species. But what you'll see in the plots, and note that the color bars there are different. I've highlighted maximums in yellow, but even though the flux out of the crater is the same, in the surroundings, you're always measuring more CO2. And so there's this sort of compositional fractionation of sorts that takes place just from that. And so I hope I have convinced or piqued your interest in rimside measurements. And one of the powerful things about combining measurements and models is that there are always uncertainties in a model regarding the source rate, other parameters. If we combine a model like this with measurements, we can help constrain some of those uncertainties, get a better understanding of some of those science questions. A couple of the most interesting things, I think, are that the composition of ejected volatiles may not be the same as the composition of the source frost, if we remember those CO2 and H2O plots. Introducing even a simple crater has an impact. In reality, as you saw in Matt's talk, local topography, temperature variations can be much more complex, and they're likely to modulate both surface flux and exospheric density in interesting, potentially observable ways. And so what I'd like to leave you pondering on is this question of what we should look for and how we should look for it, because especially at the poles, there are things like this delicate dance of molecules in the exosphere and surface that are invisible unless you look for them. And if we do look for them, there's all kinds of compelling science that can be done. So with that, I will stop.